Welcome everyone once again. My name is Karlo. I'm coming from the University of Zagreb in Croatia, faculty of Electrical Engineering and Computing. I will describe you in this presentation the paper on some desired properties of data augmentation by illumination simulation for call constancy. So I'm actually the second author on this paper. The first author is Dr. Nikola, who is currently employed in a company, Gideon Brothers. So to begin with, this is the outline of my presentation. So at the beginning, I will give you a introduction into the field that we are researching. I will mainly talk about the computational color constancy. What do we want to achieve here? What that actually is, and what are some issues that we are encountering. I will then give you some motivation for this augmentation that we have to use in this field. And so I will describe then some experiments that we have performed to see some good properties of data augmentation. And of course, I will give you a conclusion at the end of the presentation. Well, I will try to summarize the results of the experiments. First of all, you may ask yourself, what is computational color constancy? And in order to define that, we first have to define what is color constancy. And actually, color constancy is an ability which is connected to a human vision system, which enables it to perceive the colors of objects in the scene invariant to the light source color. So basically, human vision system in some way knows that there is illumination of some kind in the scene. For instance, when you are indoor, our brain knows that there is maybe a white illumination which is influencing the colors of objects in the scene. And basically, when we are talking about computational color constancy, we want to achieve the same thing, so that invariance to the light source color or illumination color in digital cameras. So actually, computational color constancy in the form of computational color constancy is implemented in image processing pipelines of digital cameras. Here you can see a simple example of what we want to achieve. So when we are capturing an image, the scene may be influenced by some illumination, which here in figure A is shown as a scene uh, affected by blue illumination, and that's something that our camera captures. So actually, camera captures image which is affected by the illumination color. And then using some method algorithm, we want to make that image to appear as one shown in figure B, where you can see that there is no influence of this blue illumination and the image appears as it was captured under a white illumination. And so that's what we want to achieve. And here, by the white illumination, we are defining a illumination that does not change the colors of objects in the scene. Uh, and how is this achieved? It is achieved in two steps. First step is called illumination estimation, and the second step is called chromatic adaptation. As you may already assume from the name of the first step, basically in the first step we are estimating the illumination from the image. So here we are given a set of pixels which represent an image, and from the set of pixels we have to estimate one or multiple vectors which represent one or multiple illuminations in the scene. So if we have only if we assume that there is only one light source in the scene, then we have to estimate only one vector. But if we assume that there are more light sources in the scene, then we have to estimate more vectors, where each vector corresponds to one light source. It is important to know that we are here working with RGB images, so our images and our estimation illumination vectors both have three channels. So one channel is red, one green, and one blue. And once we obtain these illumination vectors, we use them in the second step, the chromatic adaptation step, where we are actually dividing out the illumination from image, and we are actually doing that by the operation of division. So for each color channel, we are dividing all of the pixels in that channel with the estimation which corresponds to that color channel. So all of the pixels in red channel are divided by the estimation for the red channel, and the same for green and blue channels. And here you can see mathematical formulation of all of the computational color constancy. So you can see that our image here is represented with F. So basically, and X represents the pixel position in the image. So basically, you can see that the value of a pixel on some location depends on three functions. First function is the spectral distribution of the light source I. Second one is the surface reflectance R, and the third one is camera sensitivity for each color channel. And you can see here that our light source actually by the image formation model is different for each pixel. So it differs from based on the position in the image. The same is with this with the surface reflectance, because in each position in image we can have a different material. As I already said, our images are three components. So here F has component F red, F green, and F blue. And the last term here, this camera sensitivity. So it's basically camera dependent, and we have different sensitivity for each color channel. And when we want to estimate the illumination, theoretically, from the image formation model, we have to know two things. First, we have to know what is the spectral distribution of the light source, and second, we have to know what is the camera sensitivity for each color channel. And once we know that, we can estimate one or more illumination vectors, as I previously said. And regarding the chromatic adaptation model, this is the chromatic adaptation step. This is how it is formulated. So we have original pixel P, which has three components: PR, PG, and PB or P blue. And we have a pixel that is invariant to the illumination of the scene, which is this one on the left, PR dash, PG dash, and PB dash. And we obtain that illumination invariant pixel by multiplying this diagonal matrix with our original pixel, where on the diagonal we have 1 over the estimation value for each color channel. And as you can see here, by using a diagonal matrix, we assume here that the color channels are independent. So as I said, each pixel in red channel is divided by the estimation for the red channel, separately is done for the green channel, and separately is done for the blue channel. And these ones here in the numerators are actually denoting a white illumination, because we are defining a white illumination as a three-component vector where each component is equal to 1. And this chromatic adaptation model in this form is used to remove the influence of the illumination in a pixel, but we can alter it to change the illumination of a pixel by changing the numerator. So if we change the ones to something else, then we are actually first dividing out the estimated illumination, and then by multiplying with something different than 1, we are applying some other illumination on our image. Usually, or most often, when we are estimating illumination, methods assume that there are not many illumination vectors in the scene, or there are not many light sources in the scene, but they assume that there is only one light source present in the scene. And when the methods assume that, we are talking about the uniform illumination assumption. So basically, we assume that there is only one dominant light source in the image scene, and by assuming that, we can omit the spatial information X from our image formation model and from our illumination estimation model as well, as you can see here. So from the light source spectrum function, we can remove X, because we assume that for each X it is the same. However, we cannot remove it from the R function, which represents surface affectance, because we cannot assume that surface affectance is the same for each pixel location, because we have different objects at different locations. But here in the illumination estimation equation, we can as well omit x from the function for the spectral distribution of the light source, because we assume that it's uniform in the scene. And with that, we have to estimate only one vector E for the whole image. Unfortunately, even though we have this assumption which simplifies the problem, because we don't have to estimate a vector for each pixel but one vector for the whole image, this problem is ill-posed, because as you saw from the previous equations, if we want to estimate illumination vector, then we have to know two functions. First function is the spectral distribution of the light source, and the second function is camera sensitivity for different wavelengths of the visible light spectrum. However, when we are doing computational color constancy, we do not know these two values. Only thing that we know is a set of pixels. So we have only image pixel values, and from those values we have to estimate illumination. A simple illustration of a problem that we occur when we are estimating illumination, which is actually just an illustration, it may not really occur that often. You see here in figure 2. So basically, you can imagine this as a flat wall that is photographed, and you get a result which is on everything is yellow, so you don't have any additional information. And now, when we are looking at this, we are not sure if that was a yellow wall photographed under white illumination, or was it a white wall photographed under yellow illumination or some other combination of the light source and material, which results in this yellow color. And because this problem is ill-posed, there are many methods proposed in this field, and there are also many data sets, but as well some data augmentation is very often used. And one of the techniques which involves one of the augmentation techniques involves simulating as if an image was taken under another illumination by performing simple multiplication of the color channel values, which correspond to that chromatic adaptation model that I described. Nevertheless, there are practically no reports on the properties of the images which are obtained through that data augmentation. And therefore, our goal here was to perform for several simple experiments to get some numerical data and to see how real images should, how the augmented images should behave. And first of all, let me describe you what this augmentation is that I mentioned. So we call this augmentation through illumination simulation. Basically, if we have an original image f of E, which is taken under the light source E, and with this augmentation, we want to make a simulation of that image being taken under some different light source E dash. And basically, we are doing that in the following. For each color channel, we are dividing the pixels by the corresponding component of the original light source, and then we are multiplying them by the target light source. And that corresponds to the chromatic adaptation model, which I described at the beginning of the presentation. However, the difference of the original light source E and the target light source E dash has almost no effect on the errors when we apply moment-based methods for illumination estimation on the original image F and the simulated image F hat. But when we apply moment-based methods, we get an effect if we apply them to the original image captured under the original light source E and the same scene captured under the light source E dash. So when we apply the methods on real data, not simulated data, we see the difference. But when we apply the images on simulated data, we do not see any different in the behavior of these two methods. And And we wanted to perform some experiments where we would get more insight into how these real augmented images should behave. And in order to perform such experiments, we have to be able to obtain images of same scene under various illuminations. And we found a suitable solution in using crop dataset generator, which enables generating highly realistic simulations of raw images, which follow linear model I described in the beginning, so image formation model. Basically, crop simulates photographing a paper with printed images under one of 707 different illuminations. Here, so basically we can get the same scene under different illuminations, and we, while having all of the properties of the spectral effectiveness of the surface. And the advantage of the crop is that it has a high number of illuminations, and as I said, it keeps all of the physical properties of the material that we are using here, and that material is paper. But the main disadvantage here is again this paper, because we are restricted to only one material, so only one R we have. And to more simply describe the crop dataset generator, you can imagine it like the following. So you get an input image, you print that input image on a paper, then you illuminate that image with some arbitrary illumination from a set of these 707 illuminations, and then you take a photograph of that. And basically that's what crop dataset is doing. And a simple way to demonstrate the difference between using augmentation through illumination simulation and using crop generator, which generates realistic raw images, is in an example to apply gray world moment-based methods to images which were created with using both of these approaches, and then to compare the obtained results by measuring the error of the estimations. And we did that with that in the following experiment, which results are shown in this figure 3 here. So first we generated an image using a crop dataset generator under red light, which is shown in A. And then we modified that image using the augmentation by illumination simulation to get the image B, and we made that image to appear as it was captured under white light. Then we applied gray world method on both of these images, and we obtained estimation errors around 7 degrees for both images. Then we reversed the roles of the images, so we used crop to generate an image under white illumination, and we augmented that image using the illumination simulation to make it appear as it was captured under red illumination. Then we calculated gray world estimations and compared the errors of the obtained estimations, and the errors here were 4.6 degrees for both images. And so you can see that these two pairs of images have similar errors, but the error is different between first two images and second two images. And this is due to spectral characteristics of a real red illumination on the first image, which hides many details in the green and blue channels. While on the simulated red image, the last image, there are only slight changes, but the information is still retained in these channels, and that's why we have this error. And by this simple example, we can already see that this simple data augmentation images which are generated with this simple data augmentation can differ from realistic images that they are supposed to simulate. And with that being said, we had several questions in terms of differences between the real images and the ones obtained through data augmentation by illumination simulation, and mainly they were centered around the behavior of colors under various illuminations. So first, as you saw in the previous example, images which were obtained through illumination simulation will give a error very similar when moment-based methods are applied to them. However, in the case of images that were taken under real illuminations, the estimation error also depends on the illumination color. And the first question was, to what extent can the illumination color influence the estimation error of moment-based methods? Second, uh, while there is a significant variation in estimation errors when the illumination colors differ significantly, as shown in the previous example, for similar illuminations, the difference may not be statistically significant. So we had a question, how much does the illumination color have to change in order to also significantly change the estimation error? Uh, and furthermore, when we are using augmentation, we can use any arbitrary illumination, but in real world, cameras are restricted to a subset of illuminations, and it would be good to investigate the behavior of augmentation in both of these scenarios. So when we have any arbitrary illumination, and when we have some illuminations which are close to real world illuminations. For our experimental setup, we used so to generate data sets under some illuminations using the crop dataset generator. We have used images from volume 3 of the SIPI image database. We have used gray world and shades of gray moment-based methods. For the error metric, we use the reproduction angular error, which is basically the angle between the perfect white illumination and the white illumination we obtain when we correct our images by our estimation vector. And to generate images under different illuminations, we have used a crop dataset generator, which I described in previous slides. So regarding our first question, which is about the influence of the illumination color on estimation error, we performed two experiments. So in the first, which are quite similar, but we only use different data. In the first experiment, so for each of 707 illuminations available in the crop dataset generator, we created a small dataset based on the SIPI image database. Then we applied gray world and shades of gray methods to images, to those created images. And for each of these methods, we calculated the mean of the reproduction error, uh, which I described in the previous slide. This resulted in 707 error values for each method. So we have one error value for each method for each illumination. And in the second experiment, we did the same steps, but now we used only 76 illuminations, and these illuminations were illuminations in crop dataset that were closest to illuminations of a Q plus dataset, which is actually a real-world dataset for illumination estimation. So basically, here we used real-world illuminations. And here you can see the results. In the first row are the results for first experiment. In the second row are the results for the second experiment. Left are results for gray world method, and right are results for shades of gray method. So for the first experiment, you can see that the mean angular error spans a range of over 2 degrees, while in the where we use a very wide distribution of illuminations, and in the second experiment when we use real world illuminations, you can see that the error span is around 0.5 degrees. Furthermore, so in the first experiment, we can see that the errors are more centered inside of the range, which is a nice property to have. And this behavior is somewhat expected because in the second experiment in real world data, actually we have less variation, but again, this variation is still significant. And for the second experiment, we wondered, so how much do we have to change? How much has to be the difference between two images of the same scene captured under different illuminations? So how much do we have to change illumination in order to get a significant difference in the performance of momentum-based methods for illumination estimation? And we performed a simple experiment in the following way. So we created pairs of illuminations in the crop dataset. So for each pair of the 707 illuminations of the crop dataset generator, we created datasets using the SIPI image database. And then the per image difference in reproduction angular errors of the momentum-based methods have been calculated. Then the only information taken from each pair were the maximum of the per image differences and the angle between the illuminations which was used to generate the datasets. Then the pairs were grouped by ranges of the angles between their illuminations, and for each range the mean of the maximum differences was calculated. And you can see the results shown here in figure 5. Left are results for gray world method and right are results for shades of gray method. And it can be seen that the difference of the performance of momentum-based methods rises on average closely to linearly with the increase of the angle between the initial and changed illumination. So we can see that the larger the difference between the illuminations, the larger also the expected maximum difference in errors, which is obtained by momentum-based methods on the images which are affected by some illuminations. And with this second experiment, uh, I'm coming to the conclusion of my presentation. So basically here we try to investigate some basic properties that we should expect from the images generated through data augmentation by illumination simulation. We can see how this kind of illumination simulation does not have a significant effect on the performance of momentum-based methods, while on the other hand, when we are using real illuminations, we see that there is significant effect on the performance of the momentum-based methods. And on average, the errors of these methods for real-world illuminations can differ by several degrees, depending on the scene illumination. And in many cases, even slight changes from one illumination to another can bring a significant change in the performance of momentum-based methods, with the maximum of the expected reproduction angular error obtained on images growing linearly with the angle between the illuminations. And as a future work, since here we did only some simple experiments like a preliminary results, we would like to design more extensive tests, and we would like to explore additional ways of creating new data instead of new data which corresponds to real world data instead of using a crop dataset generator. And additionally, that crop dataset generator can be improved as well because it has only one material here. And as you saw in the beginning of the presentation, so we are using only diagonal matrix to perform chromatic adaptation, and basically we are using this diagonal matrix to perform this simple augmentation by illumination simulation. And it would be nice to investigate what are the results if we use the full 3 by 3 matrix. So if we use all 9 coefficients and not only 3 coefficients which are positioned on the diagonal. And basically this brings me to the end. So I would like to thank you for listening, and if there are any questions, I'm happy to try to answer to them.